All right, so if we're so regular logs, just background on logs. What is a log? Why do we need logs? How do we use logs? Okay, so logs are what we use to solve equations when we don't know what the exponent is. So if I'm trying to find an equation, if I'm trying to solve an equation, and the exponent is the variable, right? 2 to the blank power equals 16. You guys can do that in your head, right? 4. But what if I change this to 17, right? It's going to be 4 point something, right? But how can I get closer? That's when we use logs. That's when you use the log function to answer those questions, okay? So log 4 of 1/2 equals what? Okay, so the easiest way when I teach logs in Math 3, this is the way I teach. I teach them when you're trying to answer a log question, I teach them the loop. It's called the log loop. What you do is you start at the base, and then you go to the other side, which is blank, and then you come back around and swoop around. What? So watch. Watch what I do. Watch. Well, you have to pay attention first, right? Okay. So we started at what number? 4. And then I went to the blank, right? So we'll call that X or right. And then which value did I hit last? Okay. So what power do I need for 4 that would make it equal to 1/2? So it'd have to be a negative power, yeah. Has to be a negative power. And then I have to make it smaller. So how do I use powers to make numbers smaller? There you go. Square roots, right? Square roots. Square root is 1/2. 4 to the negative 1/2. Negative 1/2, this is a review of Math 3 logs, but means move it down to the bottom to make it positive, right? And then find the square root of 4, which is 1/2, which is what I was trying to equal, right? So that's why the power is negative 1/2. Same question for number 2, just different values, right? So the little guy on logs is called the base, right? 4 is the base. X is the base, right? On exponents, they're the big guy. The big guy is the base, the exponent's the small guy. Okay? So if I do the log trick again, I get x cubed equals 81. Well, what does x have to be when I cube it makes 81? I think I did this one wrong. No, it's not 3. I think it was supposed to be 4. I think this guy was supposed to be 4. So what number to the 4th power?
Yeah, because then that's 3.
That would be 3, yeah.
I swear something cubed in the 81.
No.
I think I messed that up, yeah. Okay?
Yeah,
That's a log. That's a log. Okay? That's a review. Okay, and then we had special types of logs, right? The LNs, we just talked about logs. When does ln come into play? When do we use ln instead of just the log?
log E.
Yeah, when it's a special type of log, right? It's a log with a base of e. Right? E. E, the value E, it's called Euler's number. Where did it come from? Came from this limit. As you plug in numbers bigger and bigger and bigger, bigger numbers, the more you plug in numbers into this limit, you're going to come close to an answer. What number are you going to come closer to? It's E. You're going to come closer to E is around 2.78 something. So as you plug in bigger numbers, 1, 2, 3, 4, 5, 6, as you approach infinity, it's never going to go above 2.78 something, which is E. Mm-hmm.
That looks like the interest?
Yeah, no, it is, absolutely, yeah. When do we use E? When we're talking about interest. Yeah, so when we're talking about interest rates or loans or anything that involves interest, that's where E is used a lot. Okay, it's easy. So like mortgages and stuff like that. Yeah, because this absolutely comes from interest rates. Okay. All right. Okay, so that's a little bit of background. Today what we're going to do is we're not going to talk about those. We're going to find derivatives of those, right? Okay, so exponentials. So exponentials look like this. When you graph exponentials, they look like that, right? Thank you. Okay, exponentials look like that. They start slowly growing, and then eventually they just skyrocket. Okay, eventually they just kind of almost grow so fast that you can't even tell. That's how things grow slowly, right? If you guys have seen zombie movies, right? It starts out with 1 or 2 zombies, and then by the end of the movie, it's like the whole planet, right? That's exponential growth. Starts off really slow, but then you know what? After a while, it's everybody. Okay, COVID, that kind of thing. COVID grew exponentially, right? I don't know if you guys remember this because it was a while ago, but everybody, when COVID started, they were saying, stop the curve, stop the curve. What the curve meant was this. They wanted to stop that. So they wanted it to flatten out or go down so that, that's what that was the big thing back then. Okay? That's what it means. So exponential grows like that. Logs grow like this. So do they grow? Yes, but they don't grow nearly as fast. Okay, exponentials are the things that grow the fastest. That we talk about, the function we talk about this year that grows the fastest. Exponentials. Logs grow, but they don't grow that fast. They grow very slowly. Okay? All right, so derivatives. What are the 3 words that we associate with derivatives? That's still the case. Slope of the tangent line is still the case. That hasn't changed. Okay? So here we go. 2 types of exponentials we're going to talk about. Regular exponential. 2 to the x power, 3 to the x power, 4 to the x power. That's a regular exponential. The one we talk about a lot more in this class is e to the something power, right? It's still an exponential, okay? So that's why I highlighted exponentials, or e for exponentials. Rarely will you see 2 to the blank power, 3 to the x power, 4 to the x power. You won't really see those. You'll see e a lot, okay? So that's why I focused on these. Logs. You will rarely see a basic log where it says log log. The logs that you will see in this class are natural logs. They're logs, but with just a special base. They have a base of e. So if a log has a base of e, it's a log, but we call it a natural log. Okay? So if a log has a base of e, we call it just a natural log. Okay? Why is it ln instead of nl, natural log? I have no clue. Okay? I have no idea. I think it probably has to do with something with a lot of these math concepts were discovered by either Europeans or what was the other one? People from, I forgot where else, Persia, I think it was, thousands of years ago. And they didn't speak English. So maybe natural log, the way they pronounce natural log was ln. So that's why, a lot of these things are, why is it nl instead of ln? Why isn't it nl instead of ln? I have no idea. But I'm guessing because of the language thing. Not a lot of math concepts were discovered by Americans because we're a very young country. We're only 200 and something years old, right? Europe's been around for tens of thousands of years, or thousands of years, I should say. Okay? Okay. All right, so believe it or not, these 2 are probably some of the easiest logs, or easiest derivatives to find. They're some of the easiest derivatives to find because they follow these rules, okay? And these rules aren't very complicated, okay? So when you see a natural log or when you see an e in this class, those are the ones we want because their derivatives aren't hard to find. Okay, for example, let's look at this one. Example 1a. Find the derivative of the natural log of 4x, right? Okay. So we go derivative.
What prime?
So log says whatever u is, put that on the bottom. So what is u
4x.
in our 4x, right? So we put that on the bottom. That's the first thing. And then whatever u prime is, the derivative, put it on top. So what's the derivative of u in this case?
4.
Reduce it if you can.
Oh.
1 over
Wow.
x. That's it. Okay. Letter B, same thing. Anytime we have a log and we're finding the derivative of it, there's always going to be a fraction first because we have a top and a bottom. Start with the bottom. I always start with the bottom because the bottom just repeats. So whatever was there already, so whatever was in the parentheses already, goes on the bottom. Just like 4x went on the bottom. So that's x squared minus 3. You can put parentheses or you don't have to put parentheses, up to you. What goes on top? Its derivative. What is its derivative?
2x.
Can't really reduce that or cancel anything out, you're done. Okay? So I think that's why they use a lot of ln's and e's in this class, is because their derivatives are relatively easy to find. Whereas if we were finding a regular log, it would be a lot more, there'd be a lot more.
10x times
No?
x.
None? Thank you, sir.
Okay.
All right, let's look at 1c.
All right. Oh.
Here's the stuff. First thing I do is I locate the stuff. The stuff we're finding log of, right? So then you're finding derivative, right? First thing you do is put the stuff on in the denominator. What goes on top? Its derivative. What's the derivative of the stuff?
6x minus 5.
Done.
Hmm.
Okay, D's right across. What's the first thing we do for D?
Oh, x to the half.
There you go, yeah. X to the half. Okay, remember, they don't have, so sometimes they won't have parentheses, but I always do the parentheses just like when I'm doing like sine or cosine or tangent or cosecant. I always put the parentheses around it because the the square root is inside the parentheses. That's going to help us later. Okay, so the first thing is, just like you guys said, rewrite it. ln x 1/2. Okay? So the first thing is rewrite whatever was in parentheses on the bottom. Find the derivative of whatever was in parentheses. So we got to find the derivative. How do we find the derivative of x to the 1/2? Yep, move the 1/2 to the front, subtract a power, we get negative 1/2, right? Now that's done, you're done there. The derivative's done, but again, that's not the way to leave it. We want to change it up a little bit, okay? So the first thing I'm going to do is, if you have a fraction on top, the easiest way to simplify that fraction is by leaving the top on top and moving the bottom on bottom. So in other words, look like this. 1, 2. Now if it's on bottom, now if 1/2 was on the bottom, you couldn't do that. But if 1/2 is on top, you can do that. Okay? And then negative 1/2 power moves down, right? So you get x to the 1/2 times x to the 1/2. What do we do with the powers? Add them together, and what do we get when we add?
X.
And over to
X to the first. Okay.
Oh, x squared.
That's the hardest part about this. Again, most of the time you guys have seen that. The hardest part about finding derivatives isn't necessarily finding the derivatives, it's afterwards. How do we simplify it, right? That's usually the hardest part about these. Okay? All right, let's look at E. So again, sometimes with natural log, they'll give you parentheses. If they don't, I always like to remind myself where are the parentheses. So it's just natural log of x. It's just natural log of x. Okay, so what am I going to do to find derivative? What do I need to do first?
Set it up.
Set it up, right? So how can I say this without giving you the answer? What am I going to use? Which rules am I going to use? Product rule, yeah, product rule. Obviously power rule, right? We always use power rule. But product rule is the big one you're going to use because it's x squared times natural log. Okay, so let's set up product. Product says the first times the derivative of the second. How do I find derivative of natural log of x?
Derivative of the inside above the normal one.
There you go, right? Put the bottom, whatever's in the parentheses, put on the bottom.
Oh,
Whatever is on the derivative of the parentheses, what's the derivative of x? Just 1, right?
Which is x.
So the derivative of natural log of x, so if it's just plain natural log of x, its derivative is just 1 over x. This one's just plain natural log of x. Okay? Now plus the opposite, right? So the second, which is natural log of x, times the derivative of x squared, 2x. Okay, derivative is done. Let's clean it up a little bit. So I get x squared over x plus 2x times the natural log of x. Well, I can simplify the powers. That becomes a 1, so it's just x plus 2x times the natural log of x.
oh, that's the answer. Okay.
Okay? All right.
Oh, speaking.
F. Which rule am I going to use here?
Perhaps quotient.
Quotient rule? Quotient rule? Is there another rule I can use instead of quotient? I could use, not the power, the product, right? So you don't have to do this. So I have some students who prefer to do it this way.
Yeah, we are not doing that way.
They prefer to do it that way because they could just use the power rule or the product rule. So it depends.
No.
You can use quotient rule or you can use the product rule. Doesn't matter. You'll get the same answer. Okay? I'll do it. I can do them both if you want me to. But I'll do quotient rule first. Since it's already set up for the quotient rule, let's do quotient rule first.
It's a high.
Yep. So low squared, low times the derivative of the high. So what's the derivative of natural log of x? 1 over x. Minus the derivative of the low, 1, times the top. Okay.
Over x. Over
Multiply.
Over low.
So x times x over 1, or sorry, x over 1 times x is just going to be 1. So you get 1 minus, and then if you distribute this guy, it's just natural log of x over x squared.
Oh.
If you were to do it the other way, so the way I do it, when do I decide? Well, I look at my answers. I look at A, B, C, D. Do they all have 1 fraction or do they have like 2 fractions? If they have 2 fractions, I'm going to use the product rule because I know that has 2 parts, right, with a plus in the middle. If it's just 1 fraction, if my answer just has 1 fraction, that's going to be quotient rule because quotient rule only has 1 fraction. So it just depends. When do you use one over the other? It really doesn't matter, but that's generally how I look at it. If I'm looking at a problem like this and I'm saying, oh, I can use quotient rule or I can use product rule, which one do I use? Look at your answers. Do they look like quotient rule answers or do they look like product rule answers where there's like 2 things, So that's how I decide. Okay. Let's see. Okay, so now E.
Speaking of,
So d dx is just do the find the derivative. Remember, this guy's an action. It's an action word, action phrase, action, whatever you want to call it.
oh,
It means find the derivative. dy over dx means here's the derivative. Okay, so let's go. So let's go back to the first page. E, things with E. How do we find the derivative of things with E? Well, first of all, what do they do first?
they just push E over.
Rewrite it, yeah. First thing you do is rewrite it. And then you multiply it times
The derivative of the exponent.
its derivative, yeah. The derivative of the exponent, that's it. So the first thing we always start with is rewrite it. So e to the 2x minus 1 times the derivative of its power, right? So the derivative of its power is just 2x, or sorry, just 2. So just move the 2 to the front. Done. Well, let's look at B. So the derivative, anytime you have e to any power, always rewrite it first. Whatever it is, just rewrite it. That should be your first instinct, rewrite. And then you find the derivative of the top, the power. Depending on what the power is, that's dependent on what rule you're going to use. Now, 3 over x, I could use the quotient rule, but it's only 3 over x. So instead of that, I think I'm going to move the x up and put a -1 there. And then I could just use the power rule. Power rule says multiply the front, take this guy, multiply, subtract a power. So I get -3, x, -2. We don't like negative powers, so we're going to move this guy down. X squared, move the -3 to the front. There you go. Okay. So everything else is just kind of more practice. It's not anything new. There's not anything where it's like, oh, by the way, no, there's none of that. Okay? So the rest of them are just practice that so like look at C, turn over the page. Look at 2C. You have an e to the x, but it's buried inside of a quotient or a chain rule problem, right?
Oh no.
If I change that e to the x to just x, you guys have done that. You guys did that last week with quotient with chain rule. Okay? So yeah, this is a chain rule problem with e involved. Okay? So actually the hardest part about this problem isn't the e, it's the chain rule part. And we've done that. We've done practice with that. Right? So anytime we're doing chain rule, we find the derivative of the outside, and then you find the derivative of the inside and chain them together with a multiplication. So the outside is something to the third power. Well, if it's to the third power, we move the 3 to the front, subtract a power. Chain. E to the x plus 3. What's the derivative of e to the x?
EX times 1.
E to the x times 1, right? Which is just e to the x. And then what's the derivative of 3?
0.
0.
Oh.
You could put 3, yeah. You would probably 3 e to the x plus. You can't even distribute because of the squared. So you can't even distribute 3 e to the x because the power is not 1, it's 2.
Oh, x times e to the x. Okay.
Okay. D, which rule am I going to use for D right next to it?
Product.
Product. Do it.
Oh. Oh, okay.
Okay.
That's an action word. Do it.
Oh, okay.
See what you get. So first, x times the derivative of e to the x, derivative of e to the x. So derivative of e to the x is kind of it's kind of like natural log. If it's just e to the x, its derivative is the same thing. Okay? So derivative of e to the x is just e to the x, plus the derivative of x, which is just 1, plus e times e to the x.
Okay.
Okay.
Oh, no.
All right. Okay, let's look at e.
I see what you did there.
All right. So it's sine of x, that's the power, right? So if we're finding derivative, e to the anything, what's the first thing we do? Rewrite. Times the derivative of the power. What's the derivative of sine?
Cosine.
Cosine.
Cos.
Done. These are some of the quicker derivatives that you'll do, but they're very intimidating. You guys walked in and saw logs and natural logs and stuff like that, right? It's intimidating. But in this class anyway, they're some of the easiest derivatives and antiderivatives that we do. Next semester, we'll do antiderivatives. Antiderivatives. All right.
Is that what he's talking about with backward?
I know. Like, he looks so
Yeah.
happy when he's talking about it too. It's like he's happy about the pain and trauma that this class gave him.
Yeah, antiderivatives is just going backward, the other way. Just going the other way. So, yeah, so with derivatives, we spend the whole semester going one step back, and next semester we spend the whole going one step forward. So it's literally the opposite steps. It's not as hard as it sounds, yeah. Once you understand derivatives, antiderivatives are really easy. That's why we spend the first semester talking about derivatives. Okay, so F. Okay, so this one's so this is another kind of tricky part. Just because it has an E doesn't mean it's an E derivative problem. I know it's got an E, but the layout of it, it's a natural log. It's a natural log problem. It happens to have E in it, but it's a natural log problem, right? This is the natural log of the yellow stuff. Well, how do we find derivative of anything with a natural log?
Derivative over normal thing.
Rewrite the bottom. On the bottom, rewrite the parentheses stuff. Whatever it is, rewrite it. And on the top, derivative of that stuff. So what's derivative of x? What's the derivative of e to the x? Done. Okay. Not too bad. Okay. All right, so let's see, example 3. Okay, so the rest, example 3 is just, you just do different things with them. Now we have a square root. So we had one earlier, I think question 1. We had one where we had a square root, but it wasn't over the whole thing, right? So this one
Well, this stinks.
is a square root of the whole thing. Right? It's a square root of the whole thing. So is this a natural log problem? Yeah, but before that, it's more of a chain rule problem because you have the outside, something to the 1/2 power, and then you have the inside, right, which is natural log of something, and then you have the last layer, which is just x. So we're finding derivatives of each. We start with the outside and work your way in. So the derivative of something to the 1/2 power means put 1/2 in front, subtract a power, chain, rewrite whatever's in there, ln of x. Now find the derivative of the green, natural log. Well, natural log is just a fraction, right? Whatever the stuff is, put it on the bottom, its derivative goes on top. So what's the stuff? X. That goes on the bottom. What's the derivative of x? That goes on top. Chain. What's the derivative of the inside? Just 1. Okay? Yeah, inside of the yellow, inside of the green. All right, so here we go. So first thing we got to do is this guy's got to move down because it's got a negative exponent. 2 is already on the bottom. You see 2 is already on the bottom? So I'm going to write a fraction. We got a 2 on the bottom. I have a square root of the natural log of x. And then I also have an x.
Oh yeah.
So what's going to be left on top?
Oh, maybe 1.
Just a 1. Done.
Oh no. Oh no.
Okay.
Aaron, you gotta stop sending me YouTube shows.
All right, B. B is, we did one with sine. Now we're going to do one with cosine. Those rules still apply. So the derivative of cosine is still negative sine. Okay? But this is a cosine problem, right? The angle, right? The angle's in parentheses happens to be a log. Okay, so we're going to treat it like a cosine problem. So we're going to treat it like it was something like this, which you've seen before. If it said something like this, cosine of 5x squared, right? You guys, we did that. We've done that already, right? What did we do first? We found the derivative of cosine, right? So the derivative of cosine of something, right? So what is the derivative of cosine? So we're going to write negative sine, parentheses, which is natural log of x, right? Chain. Then we go to the inside, right? Go one level in. One level in is just the natural log. What's the derivative of, how do I find anything with a natural log? Turn it into a fraction, right? What is it of? X. So put x on the bottom. The derivative of x is just 1. There you go. So multiply them because 1, so it's this really over 1. So you get negative sine natural log of x over x. Okay.
Oh no.
All right, we got plenty of time. So we're probably not gonna finish today, but we'll have time to do C. C is probably the last one we're gonna have time to do. And then the last 2 we'll do tomorrow, and I'll give you time to work on the practice, because the last 2 won't take us very long. Okay, so this guy. So this guy is a natural log problem, right? It's a natural log problem. Now the natural log happens to have a quotient rule situation and a power. So let's rewrite it. Yeah, it's a lot of layers here, but we're gonna take care of it.
Oh no, we're gonna have to do that thing where like we make both sides to half to the half tower.
Okay. Bless you. So I'm going to write another parentheses here because that's what I'm finding natural log. So it'll be a little easier if you do that. Do you have to do that? No. But it'll be a little easier to determine the levels. Uh-huh.
Can they not cancel out?
No, because one's minus 1 and one's plus 1. They're close, but they're not the same.
Those would not-
Okay? Okay. Anytime we're finding derivative of a natural log, what do we do? Make a fraction, rewrite the bottom.
Uh-oh.
I don't want to break this back.
Whoa, that's
So the bottom is going to have a lot to it. The bottom is going to have x squared minus 1 over x squared plus 1 to the 1/2 power.
like a Big Mac.
Now the top is its derivative. So that's where we're going to spend most of our time, right?
I'd be quaking in my boots, bro. That's all.
So over here, I'm gonna do it over here just so that I have extra room. So I got to find derivative of this. I'm going to use chain. Within there, I'm going to use quotient rule too, but it's a chain rule problem to begin with. So we're going to move 1/2 to the front.
God. Dear God.
Rewrite the inside stuff.
Steel chair.
Subtract the power. Chain.
Lodi.
Now I can get to the inside. Now I can find the derivative of the inside, which is where most of my time will be spent. Hopefully not that long. So low squared, I always start with the low part just because it's, get out of the way so I don't forget it. Okay, so low d high. So low times the derivative of the high, which is 2x, minus high times the derivative of the low, which is also 2x. Okay? Simplify. So I got 1/2. Let me show you a little trick here. So do I want to do the trick? No, I'll do it later. Okay, so this guy I'm not going to mess with yet. I need to simplify. I'm going to simplify this big fraction first. Okay? Yeah, I want to try to cancel out combine like terms as much as I can because I'm losing a lot of x minus 1s and a lot of x squared plus 1s. So that's my eventual goal, but I'm not ready yet. Okay, here we go. X squared plus 1 squared, right? So I distribute the 2x. So I get 2x cubed plus 2x. And then I'm going to, in here too, right? So I'm going to try to do 2 steps in one. So try to follow me here. I'm going to go 2x times x squared, which is 2x cubed, right? But then I'm going to distribute the negative at the same time. So it's going to be negative 2x cubed. Does that make sense? Okay. Okay.
Whoa.
And then 2x minus 1, or sorry, 2x times negative 1 is negative 2x, right? And then distribute the negative, it's going to be positive 2x. Okay.
These look pretty similar.
Okay. Cancel out what we can cancel out. I can combine those two guys, make 4x.
I think we're doing this. We have to just sit there and we don't get letters. Look at nice Greek letters, not American letters.
Man, I can't wait to get like a. I
Non-American.
can't wait to get a question. Explain
Say
4
that.
plus 2.
Because like sigma's a Greek letter, isn't it? Yeah. Sigma.
Okay.
So they have non-American letters.
Oops, 1/2. Sorry, negative 1/2. Sorry, I forgot about that. Okay, so now what I'm going to do is I'm going to distribute, I'm going to give the top and the bottom a negative 1/2 power. Because they both get it. Because it's the parentheses around all of them.
Wait, so you get we get something like something over x squared plus 1 to the derivative.
Okay. Okay, so now I'm going to multiply straight across. So I get x squared negative 1, because I get 1 on top, right? X squared negative 1 to the negative 1 half power times 4 times x. So I'm going to put the 4x here. And then you're going to put a 2 here, and then I can combine the x squared plus 1s, right?
Yes.
What do I do with the powers? Add them. So 2 plus negative 1 half is 1 and 1 half, 3 over 2.
Mhm.
That should be a 3. And then 4 and 2 simplify to be 1, 2 and 1. Okay, now that guy's going to move back home. So this guy is going to be 2x. X squared minus 1 to the negative 1 half. X squared plus 1 to the 3 over 2.
This is a bit weird.
I completely forgot the original problem.
Yeah, we had the original problem too.
Oh, we still have more to do. I did my A. Oh shoot, I should have made this.
And yeah, something to look forward to
I
tomorrow.
looked away for 1 second.
Something to look forward to tomorrow.
Then we only get done with C.
Got 4 days.
Okay.
4 layers is kind of crazy, man.
So luckily we don't have we're done with derivatives. Derivative stuff we were done with a long time ago. Now we just got to simplify it. It's actually not that bad, the last part. It just looks, because it's a fraction over a fraction, but it's not actually that bad anymore. Yeah. So tomorrow, wait, yeah, tomorrow we will finish. Yeah. So tomorrow we'll finish.